Hello everybody, good evening, good morning and good afternoon. I'm really delighted to present an IEEE Computational Society webinar entitled Multi-Objective Bilevel Optimization Algorithms and Applications. And I'm very delighted that Professor Efrén Mezura-Montes will present from the Artificial Intelligence Research Institute within Mexico. Professor Mezura-Montes is a full professor within the Institute and has published over 200 papers in peer-reviewed journals and conferences. His research interests include designing, studying and applying nature-inspired meta-heuristic algorithms to solve complex optimization problems. He has many accolades, and I won't go into them now because this is his time. So without further ado, I would like to hand over to you. And there is a question facility. If you'd like to put any questions in the chat, we will deal with them at the end. And thank you very much for attending today. We're in for a treat.
Thank you. Professor Kelly Crockett, for this opportunity to share this talk in this webinar. I'm very glad to be here. So I will start. Okay, this is my presentation, and I will show you the agenda. First of all, I will talk about my institution and my research group. Actually, particularly the two colleagues that, in very good collaboration, we developed this particular topic in a survey. I will mention that later. I will introduce multi-objective bilevel optimization because, okay, it is a known problem, but not a very popular optimization problem, I think. After that, I will briefly talk about the way this problem is solved by classical optimization techniques. After that, I will focus on the meta-heuristic approaches, which are close to the evolutionary computing area. I will briefly talk about applications, because this is an issue. I will talk also about that later. And at the end, I will discuss the findings about the state of the art in multi-objective bilevel optimization and the fertile path of the research that we detected after this survey. So first of all, I want to thank Jesus Adolfo and Alejandro, my colleagues and co-authors of this work, this survey that was already published. We are trying to be very active in multi-objective bilevel optimization, and this talk is part of this joint work. As I mentioned, this is the publication that is the base of this presentation. It is already online in the IEEE Transactions on System Managed Cybernetics Systems, and you can find further details in the paper. Okay, where am I right now? I'm in Mexico. I am in the state of Veracruz, which is this large state near the Gulf of Mexico, and my city, Jalapa, which is the capital of the state of Veracruz, is located at the middle of the state. There is a lot of mountains here, but we also have the sea very close. We have Veracruz port, about an hour road trip. And then we have mountains and we have the sea very close. So the weather is very interesting here in Jalapa. We are at University of Veracruz, Universidad Veracruzana, which is the state university in Veracruz, public university, and these buildings are our new facilities. We have less than 2 years in these new facilities. Where there is the Institute, Artificial Intelligence Research Institute. We have 2 programs, one master degree in artificial intelligence and one PhD in artificial intelligence as well. The master degree program in artificial intelligence was the first one in Mexico. It started in 1994. This year, we are celebrating 30 years of artificial intelligence in Jalapa. Okay, I work precisely in one research group, which is artificial intelligence research and applications. And there are other colleagues working on robotics and data science and Bayesian learning. This is our research group, COVNECAP, which is a union of computer vision, neural network, evolutionary computing, and applications. This is the member of my small group within the institute, Marcela Quiroz, Erandi Barrientos, Hector Gabriela Costa, and me. Okay, IEEE CIS has a task force on bilevel optimization, which is led by Ankursina and Eman Singh. This is the web page. We are trying to be very active promoting bilevel optimization, in this case, multi-objective bilevel optimization. So you can find more information about the plans that we have to give tutorials, webinars, some courses, and other activities that we have in this task force. We also have an open special issue in the IEEE transactions revolutionary computation on evolutionary bilevel optimization. In this case, this special issue is focused on evolutionary techniques applied to bilevel optimization. The deadline is in August 1, so you have time. If you are working on this topic, you can prepare a good paper and submit it before the deadline. The guest editors is Eman Singh, Ankursina, Kalyan Dev, and myself. Okay, let's talk about optimization. Optimization, I mean, we have different definitions. In this case, I take this like the way to make processes, systems, or products more efficient, reliable, and with better outcomes. That's the general goal of optimization. However, we have different optimization problems. I have to mention that this talk is focused on numerical optimization. There is important research work on discrete bilevel optimization. In this case, this talk is focused on numerical bilevel optimization. That's important to mention. Okay. I think that the most popular or the problem that has more work on it is global optimization, where we have to optimize. In this case, we can say minimize without, but you can also maximize the function. And we try to find the values of a vector of solution that, in this case, minimizes this objective function. This is global optimization, okay? We also have the problem, which is similar but not the same, where we also want to optimize an objective function. We want to find the vector of solution, x in this case, which minimizes this function, but in this case is subject to constraints. We need to optimize this objective function, but also satisfy inequality and equality constraints. This is the constraint optimization problem, also known as nonlinear programming problem, etc. So this is another type of optimization problem. I want you to keep in mind the constraints, because the constraints will be important when we define or we try to understand bilevel optimization, okay? So in this case, if I have constraints, my search space is divided in two parts. The feasible part, which is represented by these gray, dark gray areas. This is the feasible region, which is a disjoint feasible region in this case. And the unfeasible region, where we have solutions that violate one or more constraints. So the idea in a constraint problem is to locate the optimum solution within the feasible region. I don't care about solution with even better objective function value if they are infeasible. I need feasible solutions. Okay. We also have multi-objective optimization, which is a very popular, and I think it's a very mature area within evolutionary computation. If we want to solve a multi-objective problem like the one I'm presenting here, in this case, we have a set of objective functions that we want to optimize. Such a vector of objective functions can be subject to constraints as well. And we want to find trade-off solutions between or among the objectives that I'm trying to optimize. So the notion of optimum changes when we want to optimize a multi-objective problem, because we obtain a set of solutions, not just a single solution. And these ideas are very well reported in the specialized literature. Okay, so now I have more than one objective. That's important, and I also have constraints. So I have now more elements to go to bilevel optimization. Before that, this is the space, let's say the new space that I don't have in global optimization or constraint optimization, because now I have more than one function. So I have a objective function space, and I want to find the Pareto optimal set, and the evaluation of this Pareto optimal set is the Pareto front in this objective function space. That's the goal that I'm trying to reach in a multi-objective optimization problem. And as I mentioned before, this area is particularly mature and very active in the evolutionary computing area. We have now very solid, I guess, performance indicators, which are Pareto compliant, for example. Decision making is also well developed. We are able to select the most convenient solution of this Pareto front to be the one that we implement, that is the better based on some criteria. Decision making is also very well documented. There are highly competitive algorithms. NSGA2 is a very popular algorithm for to solve two bi-objective or three-objective problems. We also have many objective optimization, multi-objective optimization, large-scale multi-objective optimization, large-scale many-objective optimization problems, and so on. Multi-objective optimization is a very active and mature area. But now let's talk about some hierarchical conformation of an optimization problem. As you can see here, this is the definition of bilevel optimization. I also have an objective function that I want to optimize. In this case, I want to minimize this objective function upper f, okay? And I have a set of variables. In this case, they are divided, but again, these x and y vectors conform the whole solution that I'm trying to find. And you can note that I also have constraints, like in a constraint optimization problem, okay? However, now, one of the constraints of this upper f function is, this constraint is another optimization problem, okay? So to satisfy, the, in this case, for example, this set of inequality constraints, I can apply techniques like the one that I use in a constraint optimization problem, for example. But in this case, to satisfy this particular constraint, I have to solve another optimization problem. And as you can see, there is the x vector is also included in this optimization problem, but they are fixed values. The ones that will vary, that the values that I want to optimize in this case is the y vector. And also this nested optimization problem has can have inequality and equality constraints. Okay, so this is the idea of bilevel optimization, a nested problem. One of the constraints is another optimization problem. So to satisfy this constraint, I have to find the optimal solution of this problem to satisfy this particular constraint. So as a visual representation of the problem, we have at the upper level, the upper F function, you can see here. And at the end, I want to find the optimum of this problem. But to evaluate each one of the solution in this upper level problem, I need to go down, and with the fixed x1 value in this case, now I need to optimize this particular problem to find the y vector and then go back to the upper level, and then I can evaluate the complete solution here. And as you can note in the figure, depending of the x values at the upper level, different variation of the lower level problem can be defined. So they are different. So to evaluate the complete population, if I am using an evolutionary algorithm, for example, I need to solve one optimization problem for each one of the solutions in the population at the upper level. So it is a very costly process, okay? So upper level and different lower level problems to solve. But remember, the problem that I'm trying to solve is the upper level problem. This is a nested problem that helped me to solve the upper level. Okay, so what is multi-objective bilevel optimization? MOBO, MOBO. So it is a problem, yeah, involving one or two multi-objective optimization problems in this hierarchical structure. Okay, so okay, there's a lot of information here, but let me try to explain. We have an upper level problem, like in the single objective bilevel optimization that I mentioned before. But in this case, the upper level problem is a multi-objective problem. I have a vector of function that I want to minimize. And this upper level problem has also constraints, okay? We have constraints here. And we have a lower level problem, which is a constraint of the upper level problem, which is also a multi-objective optimization problem, where again, I need to optimize just the y vector because the x vector is fixed for each one of the solution of the upper level that goes to the nested optimization problem, in this case, a multi-objective one. So I need to solve this multi-objective optimization problem to finally evaluate each solution at the upper level. So it is the same idea as the previous problem that I tried to explain, but in this case, there is a multi-objective problem at the upper level and also a multi-objective problem at the lower level as a constraint. There is a particular case which is also very popular and we are finding that they are very useful to solve problems in different domains, which is the semi-vectorial bilevel optimization problem. In this case, I have a single objective problem at the upper level and a multi-objective problem at the lower level. So from a particular point of view, I'm solving a global optimization problem, but with a nested multi-objective optimization problem, okay? Semi-vectorial bilevel optimization, a particular case of a MOBO problem. It is important to mention some things. The goal of a bilevel optimization problem, again, is governed by the upper level. The upper level is the problem that I'm trying to solve. The nested problem is like a constraint, okay? But in this hierarchical way, I can get interesting models from different problems in different domains. That's very attractive when we want to solve a problem. And the upper level problem also have constraints and depends on the optimality of the lower level problem. Now you may think that, okay, I need to guarantee that I need the optimum solution of the nested problem to evaluate the solution at the upper level. But how can I guarantee that I have the optimum at the lower level problem? And that's a problem because we don't know, particularly in real world problems, okay? And in the semi-vectorial bilevel optimization problem, again, we are trying to solve the upper level problem, which is a single objective problem. And that's the important thing that I am trying to solve. Even if I have a multi-objective optimization problem in the nested part. Okay, so as you can see, the aim of a MOBO problem is similar to that of a single level multi-objective optimization problem. Because in a MOBO problem, at the upper level, I have a multi-objective problem. Okay, however, again, I have to satisfy the lower level optimality of the nested problem. Okay, I need somehow to guarantee that I have the optimal solution of a multi-objective problem, the nested problem, to correctly evaluate solution at the upper level. Of course, and it can be very obvious, but I think this information helps. If both levels contain single objective problems, single objective at the upper level, single objective at the nested or lower level, I am working with a single objective bilevel optimization problem, okay? But this talk is focused in the multi-objective case, semi-vectorial or multi-objective bilevel optimization. There are two positions when we are solving a bilevel optimization problem: single objective, multi-objective, semi-vectorial. It's the same. We have the optimistic position and the pessimistic position. In the optimistic position, we assume that the follower, the nested problem, tries to provide the best solution to the upper level to help the upper level problem to find a very good solutions. It's like a cooperation. But we also have the pessimistic position that expects that the lower level is trying to provide the worst value to the upper level. I mean, to make life difficult for the upper level problem to find good solutions. And these two positions are also very rich if we want to model different situations or real world problems, okay? And I have to say that the optimistic position is the most popular because theoretically is also easier to deal with it. Okay. I hope you have an idea about multi-objective bilevel optimization problem. I will move to the classical approaches, okay? This part is more of mathematical programming techniques or other approaches rather than evolutionary computing, but it's very interesting. As in other optimization problems, if I am using a classical approach, I have to assume different features that I need to find in the problem that I'm trying to solve, like this is a continuous problem, this is a differential, we have differentiability, it is a convex search space, and things become easier if my objective function is linear and also the constraints are linear in both levels. So this is a very nice figure. I hope you can understand it easily. We have, in the case of classical approaches, we have four groups, okay? And I will describe them briefly. I will start with this first group of methods. This is fuzzy methods. We detected that fuzzy logic is very popular. These concepts of fuzzy logics that are considered in a classical approach to solve a multi-objective optimization problems. We remark, for example, that the epsilon constraint method, which is a method that solves from the multi-criteria decision-making area, a method that solves multi-objective problems. Epsilon constraint is one of the most popular methods to solve now multi-objective bilevel optimization problems. However, even if those methods are already designed to solve a traditional multi-objective optimization problems, we need to manipulate the multi-objective bilevel optimization problems. And one way to do that, which is also very popular when I'm dealing with classical methods, is like single level reduction. What is this? Is transforming the bilevel problem where I have two levels, upper level and lower level, and combine them in a single level, and then I can use a traditional multi-objective optimization algorithm. Okay. Regarding the fuzzy concepts that are very popular in this particular method is the K-best method, which is inspired in fuzzy logic, for example. Okay, let's move on to the, I'm sorry, I forgot to mention that this circle represents the percentage of approaches that we found in each group. So as you can see, the most popular group in this case is the fuzzy methods. Is 47%. The second group, which is 27% of the approaches, is the penalty function methods. And this is this idea is taken also for the constraint optimization problem that I mentioned at the beginning of the talk. We also perform a single level reduction. We transform the problem from two levels to a single level. And then, and we use penalty functions, which is a constraint handling technique, very popular constraint handling technique in constraint optimization, to define a single level. And then I can use any classical method to solve this problem, okay? As I am using penalty functions, I can also use the same penalty functions to handle the constraint at the lower level and also at the upper level. And we also detected in this literature review that the branch and bound algorithm is very used in this type of problems. It was some kind of surprise about this popularity about branch and bound. Okay, the third group is the Karush-Cohn-Tucker conditions method. Again, Karush-Cohn-Tucker conditions to, for example, determine if the solution that I obtain in constraint optimization problem is an optimum, or at least a local optimum. So we can use these conditions to transform the problem, again, from two levels to one level. But it is a different transformation with respect to the penalty functions. So in this case, the KKT conditions are, I mean, they need more assumptions. For example, the solution, the functions must be convex and smooth. And it is important to mention, if I am transforming the original problem, two levels, into a single one, I am not solving the original problem. I am solving an approximation of the original problem. So this is an issue that people that work in this transformation of the bilevel problem have to justify. Okay, the third group is 70% of the approaches is the Pareto frontier generator. In this case, they try to generate solutions directly in the Pareto front of the multi-objective bilevel optimization problems. And again, the branch and bound is a very popular algorithm in this type of approaches. I have to mention that this, there are just a few words on this group, and most of the problems that they solve are linear programs, okay? Remember that we are working with classical optimization techniques. Okay, now I move on to the meta-heuristic approaches. This is the figure that we designed for the survey, where we have, in this case, 5 groups, okay? I will start with the most popular, which is the nested approach, which is 42% of the complete set of approaches. In this case, as I have two multi-objective problems, the upper level and the nested or lower level, I simply apply a multi-objective evolutionary algorithm at the upper level and also a multi-objective optimization algorithm at the lower level. There are different proposals with this idea. One of the most popular is BLEMO, which is based on NSGA2, which is a very good algorithm to solve single level multi-objective optimization problems. There are improved versions based on BLEMO. There are other versions that use, for example, quadratic approximation or surrogate models. And why? Because the nested method is very costly. Because you can think the cost that I need to assume if I am using a multi-objective evolutionary algorithm at the upper level. And for each one of the solutions in the population, I need to run another multi-objective evolutionary algorithm. So it is very costly. So the idea is to use surrogate models or some approximation at the lower level to decrease the cost of these nested methods, which is, as you may remember, the most popular way to solve multi-objective bilevel optimization problems. The second group, which is, in this case, I'm not showing the groups order by the popularity, okay? Because this second group is not very popular, just 6% of the approaches fall within this group. In this case, is the nested method, but we have at the upper level and scalarized problems. I mean, the problem at the upper level is I can transform it, or it is a single objective problem. At the lower level, there is a multi-objective problem. The computational cost decreases with respect to the nested method. However, we have a cost because at the lower level, I need to use, again, a meta-heuristic approach. In this case, for example, particle far optimization can be used. And I guess, I'm not sure, that a PSO is able to converge faster than an evolutionary algorithm. And I think that's why researchers have opted to use particle far optimization. And also, this is an inherit from the multi-objective evolutionary algorithms for single level optimization. Archiving of solution is also used in these schemes where we use multi-objective evolutionary algorithm at the lower level. The third approach in this case is nested method with scalarized lower levels. In this case, the multi-objective problem is at the upper level. At the lower level, there is a problem that is a single objective. Okay. It is less expensive than the previous two groups that I mentioned, because now the costly, the source of the computational cost, which is the lower level solution, it is less expensive because I have a single objective approach. In this case, and as you can see, there is a more diverse set of algorithms that have been used to solve the upper level problems. Genetic algorithms, particle optimization, BLEMO, for example, is also used just at the upper level. And I guess popular names like MOEA-D at the upper level also appear in this group. NSGA2 is also very popular to solve the upper level problem. And again, the problem at the lower level is a single objective problem. I can use any technique depending on the characteristics. So the problem, if the problem at the lower level is linear, I can use linear programming. It's less costly than an evolutionary algorithms. Or if the problem is costly, I can use surrogate models. Okay, I move now to the group number 4. In this case, I have both levels scalarized. I have multi-objective optimization problems, but I solve them in a single objective function. So I use the weighted sum approach, which is also a very popular way to solve single level of multi-objective problems. But in this case, I need to solve the upper level problem as a scalarized problem, and also the lower level and as an scalarized problem. And finally, this group assume that we can apply a reduction of the levels. I mean, the same idea that we mentioned for the classical techniques, we can now use it here to transform the problem, multi-objective at the upper level, multi-objective at the lower level, in a single level multi-objective problem, okay? And then I can use the algorithms that are very popular for single level multi-objective optimization, like NSGA2, MOEA-DDE, and others, okay? Karun-Kostuker conditions can use to transform these two-level problems into a single level problem, okay? So this is a bird's eye view of the efforts that have been made to solve multi-objective bilevel optimization problems, both from the classical techniques and the approximate technique, like meta-heuristic approaches. So regarding applications, there is still not too many applications to report. There are some domains that multi-objective bilevel optimization is more popular, but I think we need to work more on applications. For example, manufacturing industry. In this type of problems, we have a hierarchical structure. So if you model your problem as a multi-objective bilevel optimization instead of just a multi-objective problem, you can find solutions that can be better at the end, okay? Also, logistics has some applications. All these, the details of this application are reported in the survey and also in the supplementary material. In this case, again, this hierarchical way to model problems is very helpful to solve problems in this particular domain. And another set of applications are in environmental economics, how these financial implications policies affect the environment, okay? And I have to mention, in my group, we are working in the mechatronic and automatic control area. We are finding very interesting results if you model the same problem as a multi-objective problem, traditional way, but now as a multi-objective bilevel optimization problem. So the type of solution that you obtain and the opinions that we are getting from the expert are very, very interesting, because the type of solutions are, I mean, the bilevel way to solve the problems gives you some advantages about the traditional way to solve problems. Okay. Discussion and future trends. What we can summarize from this literature review about multi-objective bilevel optimization? There are several benchmark problems. Some of them are very easy to solve. Some of them are linear, and because they come from the classical optimization area. But not many real-world instances. I think we need to work more on that, and I think it's a fertile path of research. The nested approach is very popular, but it's computational costly. So you can have very good solution, but the time to get one good solution is very, very large. Single level reduction is very popular, and it helps particularly for classical problems. Sorry, for classical optimization techniques. But the problem must have particular features if you need to perform this transformation. And again, you are solving not the original problem, but a transformed problem. We are very limited in the number of objectives. Up to 3 objectives, problems are solved. And as I mentioned before, in traditional multi-objective optimization literature, you have large scale, many objectives. Here, just 2 or 3 objectives. And also, regarding the dimensionality of the search space, some problems has 20 variables, and that's the large scale in this particular problem. Constraint handling, we have constraints. Also, as I mentioned, the nested problem is a constraint, but it is not a lot of talk about constraint handling in bilevel optimization. So more focus on this type of designs are expected in the future. as for example, nowadays, constrained multi-objective optimization is a very active area. There is a lot of proposals about that. I think a similar phenomenon will occur in the coming years now for multi-objective bilevel optimization, because as you can see, constraints are also considered. Performance indicators. I mentioned that the problem that, the real problem that I'm trying to solve is the upper level problem. However, if you want to measure the quality or the behavior of the algorithm, it is not enough to apply performance indicators at the upper level. They are not applied at the lower level. So we need to think on different ways to measure or apply indicators, not just at the upper level to analyze the quality of the solution. A priori and a posteriori decision making are very popular in this type of problem, but the interactive decision making hasn't been explored. So we need to go further on that. And I don't know if you know a problem in the bilevel multi-objective optimization problem. What happened when I have at the lower level a multi-objective problem, I will obtain not just one single solution. I obtain the Pareto optimal set, a set of solutions, all optimal. What is the one that I need to choose to send to the upper level to evaluate the upper level solution? The most common way to do that is, okay, I have all the Pareto optimal set. I pass all the Pareto optimal set to the upper level. I evaluate all the solutions, and the best one will be used at the upper level. But it is very costly, because I have to evaluate all of it. So is there any other better way to do that? I'm about to finish my presentation in case there are some questions. This is the website that we are maintaining with Jesus Adolfo and Alejandro. You can consult it whenever you want. It's by-level.org. You can find tutorials, you can find codes, you can find a repository of algorithms, benchmarks, etc. So you can also, besides reading the survey, go into the website to have more information about our work. Okay, what are those interesting future works? We need more theoretical studies, optimality conditions, but not only on linear problems, but also in non-linear cases. Performance indicators at the lower level, they need to be applied. Maybe we need new designs, new indicator designs precisely for the bilevel optimization case. Nested methods are very popular, but we need to deal with the cost. We need to propose good techniques to decrease the computational time that they require. In the single level multi-objective optimization, we can find Pareto-based evolutionary algorithms, decomposition-based evolutionary algorithms, and indicator-based evolutionary algorithms. If you remember the names of the algorithms that I mentioned that have been applied to solve multi-objective bilevel optimization problems, I haven't mentioned performance indicator-based algorithms, like SMS-MOA, for example. We haven't seen the application of this type of MOAs in multi-objective bilevel optimization. We need more challenging benchmark to really assess the capacities of the algorithms that we already have, or if we need to design more complex algorithms. The problem that I mentioned, the decision making at the lower level. How do I need to perform a more efficient way to select from the Pareto optimal set at the lower level the solution that I will use at the upper level. We also need to analyze the impact of feasible solution set from the lower level to the upper level. What happens if I cannot find feasible solutions? Remember that the lower level problems also have constraints. And finally, we need more real world application. As I already mentioned, the work is more focused on benchmarks rather than real world applications. This is social media for my institute in Jalapa. The information is in Spanish, but there are ways to translate the information. Otherwise, if you are interested in more in the Artificial Intelligence Research Institute in Jalapa, I can give you more information if you write me an email. We are in Facebook, we are in X, and we are in YouTube with a channel which is called Código AI, AI Code, which is a channel that aims to socialize artificial intelligence. And that's it from my side. I will be happy to answer questions. Thank you very much.
Wow, thank you so much for a really, really exciting talk. I'm going to ask attendees to put some questions into the chat, into the questions tab. Let's get that right. And just while people are actually thinking about the questions, can I just ask you something about a real world potential application? Okay, so I'm really interested in measuring the ethicalness of any kind of algorithm. And in the past, I've used traditional optimization techniques that we're all familiar with, GAs, ant colony optimization, you name it, to do parameter optimization for algorithms. And obviously, this isn't my speciality. But I've been talking to people about looking at things like fairness metrics for algorithms, bias metrics, etc., even metrics from explainable AI. Do you think there is a way to apply multi-objective bilevel optimization techniques to optimize not just traditional things like, say, accuracy, specificity, etc., but to also look at those as individual components, fairness, explainability, bias, etc.?
Yes, I think this is thank you for the question and the comment. Yes, I think that this, again, this let's say new way to model a problem in a hierarchical way can lead you to include other aspects that when you deal with a traditional single objective or multi-objective problem, single level, you can do that, but the type of solution that you obtain are not the one that you are expecting. So giving a chance to this type of models, and again, we are working more on the mechanical design area, at least in that area, we are finding that this type of solutions that we obtain provides you some advantages of those that are obtained from a traditional model or traditional optimization process. So yes, I hope the community will be very active on adopting this type of models and designing good algorithms to find solutions. But definitely, Kelly, this is a very promising part of research.
No, it really, really sounds fantastic. Although I'm waiting for some questions to come in. There's nothing there yet. So I'm just going to carry on that line. It was really interesting discussion saying, yes, if you've got a mathematical metric like you do for algorithmic fairness, which is fine, there are even metrics that exist, how good they are, I'm not convinced, for bias from a mathematical point of view. But then we talked about, well, what happens if you throw a measurement of human unconscious bias into the actual mix? And it's really, really interesting. I'm not sure how it would work, but it's definitely something I would like to explore. So come on, you attendees, please feel free to ask a question.
Yeah, don't be shy.
Yeah. So I guess the other thing, while we're just waiting, the other thing I'm going to say is you talked a little bit about the gaps in the knowledge and the things what needed to be done. What's the one big thing you're kind of working on in this area at the moment?
Okay, in applications. we detected that there are not many applications.
Yeah.
We moved to the mechanical design area, automatic control, and also we are trying to deal with neuroevolution or neural architecture search. It is a very expensive problem, and modeling as a bilevel problem is also expensive. So we are the worst of two worlds in the same problem, but we are trying to determine if the type of artificial neural networks that a bilevel problem provides also have difference with respect to the other way that neural architecture search is performed. So again, you can try any domain. That's the good news. You can, if you have some solution in a particular domain when you solve the problem in a traditional way, give a bilevel optimization a chance, and maybe you can be surprised.
Yeah, and guess what? We've got some questions coming in now.
Right.
So the first one is from Catherine. Thank you, Catherine. Can you talk about the benchmark problems that you have on the bilevel.org site? And also, are they artificial or are some real world?
Yes, we code the benchmark that was proposed with BLEMO, which is one of the most popular algorithms. We coded in different programming languages to make practitioners easier to adopt the code. We don't have real world problems. That's an issue. But again, with this attempt that we are trying in different domains, the idea is to generate a real world problems benchmark and to generate or use the existing algorithms to solve the benchmark problems and also the real world problems and establish differences, because this is very important. There is always a gap between benchmark problems and real world problems. But in bilevel optimization, we have very few information about that. So this is a work in progress. But yes, you can find the traditional benchmark problems codes in the website. If you have a problem, let me know.
So Catherine says, thank you. So there is an opportunity there, especially for anybody watching this back or on this call who's got a real world problem that might be applicable, to actually drop you an email and see there could be some potential collaboration there, which is absolutely fantastic.
That would be very
I think I might certainly be doing that. So yeah.
yeah. We'll be very happy about that.
Yes, it's really interesting. Okay, so I do not think we have any more questions that are coming through. So without further ado, I would like to say thank you so much for giving your time and this fantastic webinar and sharing your knowledge.
Thank you, Kelly, for all the help to give the talk today, and also for Professor Malan for the invitation. I'm very glad and always ready to serve in IEEE Computational Intelligence Society.
Absolutely, and look forward to meeting you in person at Wiki.
Okay, that will be very nice in Japan.
Yes, absolutely. Yeah. Thank you so much. Right, everybody, thank you, attendees. Watch out for the next webinar that's be circulated soon. And thank you all for attending. Thank you.
Thank you. Okay, I think that's it, Kelly.
It is, yeah. I'm just working out, just stopping recording.
Oh, okay.
I'm hoping Joanne will let it.
Sorry. Okay.
No, you're fine. I'm learning. No, you're okay. I'm just going to work out, make sure that we stop.
So I can stop sharing my screen.
Absolutely. Yeah. Okay. Thank you so much.
Okay.
Right. Thank you.
Thank you, and I hope to see you in Japan late June.
Absolutely.
Okay. Thank you, and thank you, Joel, and also for the help.